Um, I will make this presentation, which is the result of a collaborative work. This work is carried out within in an internal project, which focuses on finding out how these large language models learn different NLP small tasks. And the focus of this presentation is how they learn part of speech tagging, especially for unknown words. So, okay, just a moment to adjust a bit. Good. So it's this era that we are living today of large language models, of transformers especially, that have changed a lot the way in which NLP algorithms deal with with language analysis. And with this attention mechanism, a word-to-word matrix of linguistic relevance, morphosyntactic and semantic, that is learned from raw texts, these models appear to learn, we say, any language when trained on billions or even trillions of words. When we fine-tune to an NLP task, for instance, post-tagging, named entity recognition, dependency parsing, or others, the transformer models achieve state-of-the-art performance, and so they behave quite well. But why exactly are these models so good at seemingly any NLP task? This is a question that we, or most of us, ask, but the research on this topic is scarce at the moment. With this presentation, we add to the research explaining the inner workings of transformer models by conducting a cross-model study of the post-tagging capacity of these models. More exactly, we aim to provide empirical evidence supporting the hypothesis that transformer models learn the post labels of unknown words, which are words not seen during the training phase, and investigate if there is a cross-model similar learning behavior when it comes to learning part of speech labels. The presentation of the experimental setup now. We use the available Romanian bird model from Hugging Face. They come in three different, so there are three different models, actually, the small, the base, and the large one. And there is also a bird model available that was trained on Corolla, which is the Romanian reference corpus, which contains texts from different styles, genres, written and spoken language of contemporary from contemporary data, which covers more than 1 billion words at the moment. And what we do is to fit the output layer of the bird models with a post-tagging head with 35 morphosyntactic categories. And we fine-tune this augmented model by training on the Romanian reference tree bank, which is a tree bank annotated according to universal dependencies principles. Those of you who are familiar with these tree banks know that all or most of the corpora which have a reasonable size within this project are split into three parts: the training, the dev, and the test sets. And for Romanian, for which the corpus has about 210,000 tokens. The training corpus contains about 185,000 tokens. And here we use the dev and the test parts together for testing. So about 33,000 tokens. The starting learning rate parameter is set at 10-5, and it is decreased by a factor of 0.9 every epoch. And there are 5 training epochs in the experiment. And we compare the accuracy on the POS labeling task for unseen words versus words that are rarely seen using the odds ratio statistic. We noticed that rare words are mostly content words, so nouns, verbs, adjectives, and adverbs. And to make the comparison between unseen words, so those that have frequency 0, and rare words fair, we will only consider evaluating part of speech labeling of content words. This is in this table we have the distribution by frequency for the test set, so the dev plus test set in the UD3 bank. So we have about 3,000 words, content words that have 0 frequency here, so unseen in the training set. And F1 means only one occurrence, more than one occurrence in this. Now, we use this odds ratio to measure how likely it is that the accuracy of POS labeling of unknown words, so not seen during training, is alike the accuracy of known words, those that are seen during the training phase. Our claim is that if the transformer model does indeed learn the part of speech of words, it should be as accurate on unseen words as it is on unknown words. And the odds of being correct is calculated as the probability of being correct, so the accuracy divided by the probability of being incorrect, the error rate. The odds ratio between unknown words and between known words and unknown words is calculated as the odds of being correct on known words divided by the odds of being correct on unknown ones. So the odds ratio should be around 1 to verify this claim. So what we see here, this print shows that Isaac was actually chosen only for the results obtained for Robert Small, so the small data set. But the results for all 3 data sets are actually similar. That's why we chose to present only one. In orange here, you can see the low value of confidence interval. In green, the high value of the confidence interval. And what we have in blue is the odds ratio between known words with shown frequency, so F larger than 0, and unknown words, those with frequency 0. And we see that the odds ratio is between 1 and 1.4. These are the results when using the model that was trained on our corpus, on the reference corpus. And here the odds ratio quickly rises above 4, which means that can do better parts of speech tagging only on seen words. And these are actually some results that that are similar to models that are undertrained. And that's because of the difference in size of these data sets that were used. Well, when looking at a cross-model behavior, the research question is, are there dimensions of the BERT output vectors that are the same across models and that are responsible for the learning of a particular part of speech? And for the comparison in this experiment, we used 2 BERT models with the same number of output dimensions, namely 256. This was the Robert Small and the BERT that was trained on Corolla. And for each word in the test set, with its part of speech category, we extract the top 10 dimensions of the BERT output vector that contribute the most numerically to the classification of the part of speech category. And for each part of speech category and dimension D, we compute the conditional probability over the whole test set, and we sum it over the common dimensions of each category. The dimension overlap probability mass is small, which means that the part of speech information is not encoded in certain dimensions in different models. And from these small experiments, we can confirm that properly trained BERT models learn the parts of speech labels of unknown words by obtaining the same accuracy on unseen words as on known words. We could not replicate the learning behavior of part of speech labels across BERT models. And this part of speech information seems to be encoded differently in different contexts of the same word with a given part of speech. And there seems to be an optimal number of parameters of the model that best suit part of speech label learning. And in our case, the best model was Robert Pais. So not the larger model, but this Pais, let's say, version of it. I was quite quick. And that was the whole presentation. And unfortunately, if there are technical questions, I cannot answer them. So I urge you, because in this presentation, only a few of the results were presented. Some more tables and figures are presented in the paper. If they are not sufficient for your understanding, I urge you to address the first author, my colleague Radu, whose email address is available in the paper. Thank you for your understanding.